A changing magnetic field in the proximity of a conductor, or in this case, two conductors, has some very special effects, and it's something that people don't really think of, something that just passes by as nonsense. In this case, the red wire is indicating a single wire, the black wire is indicating a single wire, and the two wires are parallel. The two wires almost are connected together except for the insulation. The two wires can act and react together. They have a relationship because of the proximity that they're in, and they also have a relationship because the current that they potentially might carry. The current would normally be thought of as in one direction, and I'll show you that. So in this case, the wire is being shown, so wire A, the black wire B, the red wire, and in this case the current would be in one direction. So we would see a changing magnetic field externally, not shown, would induce an EMF on the ends of the wire, and when the wire is connected to a load, the current would flow. The current would flow in the same direction at all times, would never change because of the fixed conduction. Basically, what I mean by that is the ends of the wire are fixed. There's no change in conduction or change in current relative to the two wires independently of the changing magnetic field. So basically that means that the current and the voltage on this wire would stay the same at all times, would never change. Polarity and phase would not change unless the external magnetic field was changing with it. The external magnetic field is the driving force. Lenz's law obviously would apply, and both of these wires would carry a current which would be equal and opposite to the changing current of the source magnetic field. Now, if we were to change that, if the situation were to change, if the relationship between the two wires were such that the relationship between them could change, meaning the conduction at any one time would have to change, and the magnetic field that's changing externally would be still a driving force, but the proximity of the conductor, because they're so close together, would have an effect. So what we essentially are trying to do here is we're trying to change the currents. Instead of both going the same way, current B wants to go the other way. So we want the same as the Mr. Prever experiment. We want the current to be equal and opposite between the two wires. It's a situation that we have to invoke. We have to invoke this this situation. It's something that won't happen unless we change or do something to make this change. We've got an external magnetic field. L2 is the black wire. L3 is the red wire. Now, at any one point in time, these two coils at the top would have the same conduction, same polarity, same phase, as long as Q1 is switched on. So the induced voltage between the two coils would be the same. Now, at a particular point, if we were to interrupt that conduction on L3, the reaction of this interruption between L3 and L2 would have an effect. So what we would potentially see is possibly a spike. So depending on our conduction and the timing and everything of our interruption, the spike here would be seen on the wave. So essentially we've still got our electromagnetic induction happening from our primary. Voltage and current would still be the same at least on L2. So L2 wouldn't potentially change. There might be some harmonics and stuff come through on that wire, but potentially the voltage and current would stay the same. We would see a big spike. Now what's going to happen here is if we interrupt the conduction close to the peak of the cycle, we've got two wires that are carrying current, and then all of a sudden we interrupt one of the wires, then the magnetic fields between the two wires would effectively slap together. We have a Lenz law effect if the timing is right, if the switching is right. Have a Lenz law effect where the currents would flow in reverse. So we would see a spike, and this spike is the change in magnetic fields. So as soon as we switch, the faster the change in the magnetic field between the two wires, the higher the voltage will be. So remembering that voltage is the change in magnetic field, and current is pumped by opposing magnetic fields. And what I mean by that is I've actually explained it in one of my last forum posts, but what I mean by that is if we had a wave here and all of a sudden we were to immediately have the primary disappear, then we would see an inductive collapse. So anything that's above zero is like a DC switch. So effectively, if you have a DC switch, magnetic field grows. If we're not supporting the magnetic field anymore, instantly, if we instantly turn it off, then the magnetic field will collapse. And the interesting part is we have energy around the conductor, okay, and the potential energy comes from the immediate space, the near field around the conductor, and I'll show you that now.
Now, we've already noted in the case of that exponentially decaying dipole that energy gets stored in the near fields around an antenna before it's released. It gets pumped into the near fields and will hang around there for a quarter or a half period and then decouple and radiate away. And interestingly enough, that had been observed at least as early as Oliver Lodge in 1907. He noted that the effective source of electromagnetic radiation isn't at the oscillator or the antenna itself, but he described it as being about a quarter wavelength in advance of it. And he noted that Hertz found that also to be the case. That's looking at those phase plots that Hertz.
Okay, so we know that a coil is basically an antenna. If a coil is in resonance, it's doing the same job as what an antenna does, basically. Antennas are quite complex. The antenna theory is pretty full on, but it's perfectly understandable if you spend enough time studying it. Don Smith said coils are antennas, and I'll link to a video there as well.
Okay, whenever you get into wave type arrangements, you have half waves, quarter waves, eighth waves, and so on and so on. So basically what you want to do on any turns or whatever you put on your second coil, they should be a relationship such that it will be either a multiple or a division of the same frequency. The second coil is going to run at a different frequency because the wire length is different. Coils are actually antennas that have been coiled for convenience.
But we need to think of the current, the change in a coil in proximity to another coil. And what I'm showing here is basically we have our two coils, okay, and end A over here. So these two coils, the two terminals on the end of the coils, end A, Okay, at the other end is NB and B. These two ends are basically tied together. So essentially the connection, the terminal is connected at each end into one terminal, as we saw in the transformer, and then connected to a load. So up here is the tied together terminal. It is connected to a load, and we also see the same on this side. Pretty straightforward. There's really not much to it. So what I want to show here is I want to show the difference in current flow between this coil and this coil. Okay, and remembering these two coils, they're partnered output coils. They're two coils effectively magnetically coupled to each other. Now, as long as there's no difference in conduction between the ends of these coils, if the conduction stays the same, if none of these coils have broken conduction, then these two coils, their currents and voltages will stay the same. The phase, everything else will stay the same. And remembering, with this experiment, we have a changing magnetic field in the proximity of these two coils, which is not shown. So the magnetic field is quite strong. We have a pretty reasonable EMF generated on these coils. So just remembering that. Okay, so if we run a quick simulation, this is terribly inaccurate, but it gives you an idea. A quick simulation, we can see we have a difference. Okay, this coil up here, which is not a coil, it's a straight wire. And remembering, these coils are imagined as straight wires, parallel straight wires that are connected to each other. So these two coils have a difference in conduction. At this stage, the switching time of this MOSFET is changing the conduction of this coil. Remembering, MOSFETs have internal diodes, so the direction this way from end B to end A will conduct via the diode. So there is a diode in there, the current will flow that way. Once the voltage on the diode has reached avalanche, and it's 0.44 volts or whatever it is. So if we sort of fiddle with the conduction here, so we go to say 3 Hertz, and you can actually see there is a slight difference. You can actually see, and remembering this is a terribly inaccurate depiction, but you can see that the flow of current does change very slightly. Okay, so we have different colors here and here, and we have different flow rate here and here. Now these simulations are not magnetically coupled. All I'm doing is changing the conduction here. So remembering, these will be much stronger effects because of the magnetic coupling between these two wires. Remembering this, there's the change. So every time this coil has a current flowing through it, and every time this coil here has a current which is chopped or disconnected, the change that this coil makes in proximity to this coil here will cause very high voltages. And once the high voltage is reached, if we can hold the conduction of this wire at the right time, then we get a very special effect. Okay, the effect that we've studied already, the effect that we've sort of talked about for quite some time, is the change in magnetic field. We've just discussed that the faster the change between the two coils, the faster the coils slap together, if you like, the higher the voltage which is gained. Now, at the peak of the voltage, that's where the most potential in the coils can be held. Now, what I mean by that is there's a couple of actions that happen as the coils slap together. It causes a voltage, and normally we wouldn't want the voltage. Normally we want to try and filter the voltage out and dump it to ground. But in this case, what we're doing is we're using the very hard slap of magnetic fields between the two coils to create the voltage, you can hold the coils at that stage. Because you have a high voltage, you can hold the coils in effectively what would normally be thought of as a dead short situation. Now, the dead short situation is effectively like the neodymium magnet being dropped down the copper tube. At that stage, you have a linear decrease of magnetic field over time. You've got to remember you have three things all in the same area at the same time. You have your two coils, which both have a potential voltage on them. You have a current in at least one coil flowing, and you have a magnetic field at the same time. So there's the three things: your magnetic field, your coils, your current flowing as well. Now, the current flowing is really important because if you don't have current, you can't use the magnetic fields to slap together, because the harder they slap together, the higher the voltage. It's the change, the time rate of change of the magnetic field that creates a voltage. It is the opposition of magnetic fields or currents that pump current. We have effectively a means of pumping current by having an opposition of current. The current must buck, where you must have opposition of current to actually pump current. It's a little bit like the railgun scenario. We have the small magnet that's put in the channel, and the big magnets obviously push it through as fast as possible, accelerates very fast. Now, the acceleration is very important because that's actually what Don Smith told us. He said that his machines were electron accelerators. We must remember that every single electron is in itself a small magnet.
The devices which I have invented, which there are a number of them, they all actually accelerate electrons. Okay. They're electron accelerators.
The electrons, if you want to go with whichever scientific theory that says they move at 1 inch an hour or whatever it is, at the end of the day we do have current. So whether it be the electron or whatever it be traveling through the wire, it is a current. There are bodies with mass that have magnetic fields when they move, and at the end of the day, that is kinetic energy. The current is kinetic energy, and with any kinetic energy, the inverse square law, in this case because of the magnetic field and the charge, can be used in a fashion to actually accelerate the bodies in motion.
Hey, I'm Anthony.
And I'm Andres.
And thanks for watching our video. We know you guys have a lot of questions to ask, and so this is what we made that video for. So to start off, the magnets are called neodymium and ceramic.
Yeah, well, starting with the neodymium, this is a ½ inch long on each dimension. They're cubes. And then for the ceramics, it is 1 by 7/8 this way, 3/8 this way, and then 7/8 this way. So just want to clarify that. Okay, then onto the wood. This whole wood structure here is 24 inches long. It's 24
right here. 24 inches.
Yeah, and then
these are about 23 inches because this part right here, they don't extend the full length, so that way we could keep these in place, the rods in place.
And pretty much we've been getting a lot of questions about these. They're just rods. There's nothing real special to them. They're just wooden rods.
We just put a lot of graphite on them.
Yeah, that's why they appear like to be silver a little bit, just because we've graphited it a lot. Then they just slide in here.
And right here, if you can see these little circles, we drilled holes in these because you can't really use metal screws or metal nails in this situation because it'll throw off the magnetic field. So what you want to do is we used circular dowel rods and then just place them inside with like a rubber mallet. That way you can get it all stabled out.
And then we just cut the excess off.
Yep.
Okay, and then for these ceramic magnets, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 of them. Yes, there's indeed 18. Okay, and then to get these ceramic magnets in place, we use this double-sided tape here. We pretty much just laid a bunch of strips down and we just pressed the magnets in place, so then they just stayed. And then for these ceramic magnets, to line them up, the angles that we lined them up were, it was a 45-degree angle from here. There's a 45, like it's a 90-degree angle, 45, 45. So then after we set that one in place, we use that as our marker to line up the rest of them. So that's that. And then this is 5.5 inches long this way, and then this tiny chamber right here that we use to put the magnet in, it's 5/8 of an inch. So the magnet just barely fits in. So I'll leave your comments and questions below. We'll get back to you as soon as we can, and stay subscribed to our videos. That way you can see our upcoming videos, including the levitating magnet.
It's a very interesting theory, and obviously we have experiments to back up the theory as well. So don't forget your current in your wire. Conductivity is so important. The fact that we have a piece of wire that can conduct, effectively have a flow of electrons or a flow of charge run through the wire. It's a conductive element that we can change at will. The conductive element is the key to moving forward with this technology. You've got to remember, we're building a pump, and it's very simple. The pump is so simple, it's just not funny. At the end of the day, you've just got to catch the wave. And what I mean by catching the wave is simply that the coils themselves must interact together in such a way that the voltage is built up, and then once the voltage is built up, we must hold the currents. So effectively the L2 and L3 coils, they must hold the currents high when the voltage is high. Got to remember the Ohm's law. So I equals V over R. So the higher the voltage through the resistance, the higher the current will be. If we can increase the voltage, then the current obviously will increase as well. And remember the experiment that we proved that current can be pumped and that current must be supported. Floyd Sweet went through and started talking about that in a paper as well, where it didn't really make much sense in the Nothing is Something paper. But anyway, the current must be supported. So in a sinusoidal wave, the sinusoidal current must oppose at every single stage of the cycle. If there's no opposition, if the opposition to the changing magnetic field is dropped, then at the end of the day, the current will drop as well. We will see inductive collapse. Anything above zero must fall back to zero. Equilibrium, pretty straightforward science there. Anyway, this is probably getting a little bit long, this video, so I will end it here. I hope it makes sense, and I hope we can sort of get through the few little ideas that I'm trying to share here. It's a bit broad, so good luck. I hope everything makes sense after this video.